Welcome to the deep dive. When you think Nikola Tesla, what probably springs to mind is that eccentric genius, right? Wild hair, maybe some lightning bolts.
Yeah, the classic image.
But today, we're aiming to look, well, a bit beyond that. Because Tesla's real genius, it's not just misunderstood. Sometimes it feels like we miss it entirely because we're using the wrong lens.
That's a great way to put it.
So we're diving deep using a pretty unique perspective, something we're calling motion theory. And this isn't just, about things moving. It's really about seeing Tesla as this ultimate synchronization engineer.
Ah, I like that. Synchronization engine.
Yeah, like he didn't just get motion, he practically conducted it, played it like an instrument.
He really did.
So our mission for you today is to get a kind of shortcut, a genuinely fresh way to see how Tesla's whole body of work was fundamentally about phase, rhythm, and field geometry.
Core concepts for him, absolutely.
And you'll see how this is still so relevant. It shapes our modern world in ways we barely even think about. So get ready to hear that familiar hum from the grid or, the spin of a motor in a totally new light.
Should be interesting.
Okay, so let's unpack this. When we think Tesla, those dramatic lightning bolts, the kind of wild experiments, they really dominate the picture.
They do. Makes for good stories.
But our sources suggest something, much deeper, more elegant, actually, right at the heart of his work. So how does this motion theory really help us see him differently?
Well, it's fascinating because Tesla wasn't just calculating motion in the way, say, an engineer might calculate stress or strain. He was conducting it, actively shaping it.
Conducting it. How so?
Where other people just saw wires or maybe static fields, he saw these dynamic things: phase, rhythm, field geometry, the actual patterns of movement.
Okay.
So he was fundamentally this engineer of resonant reality, a master of synchronization engineering.
Right.
Think of it like this. He was figuring out how to shape matter, how to arrange things, so that motion itself would just lock, rotate, transfer, and amplify without anything physically touching.
Without contact. That's key.
Yeah. If you think about Faraday, maybe he made field motion visible, right, through his experiments. And Maxwell gave it these beautiful equations.
A mathematical framework.
Exactly. But Tesla, he kind of learned to play it like a musical instrument. He found the notes, the chords, the resonances.
That's a really powerful shift. But maybe for our listener who, gets the basics of electromagnetism, what is motion theory fundamentally? How does it reframe things?
That's a really good question. It's crucial, actually. At its core, motion theory suggests that these fundamental electrical things, fields, currents, even how matter behaves, can be understood as emergent patterns of motion that's either synchronized or desynchronized.
Okay, so patterns of motion.
Yeah. It shifts the focus from just static forces or thinking about electrons simply flowing like water to these dynamic, rhythmic interactions. So energy transfer, in this view, isn't just about how much voltage or current you have. It's deeply about aligning the rhythms, creating or managing sort of gradients of synchronized motion. So when we use terms like phase or field geometry, we're really talking about the precise timing and the spatial arrangement of these underlying motion patterns.
Got it. So it's about the dance, like you said, not just the dancers. And his most famous invention, AC, that really fits this, doesn't it?
Perfectly.
Back in the 1880s, DC power, direct current, it had that huge limitation. Energy just dissipated over distance.
Yeah, you needed power plants practically next door.
So how did Tesla's AC leap solve this? Not just practically, but in this motion sense. You called it phase choreography.
Right. Well, the practical genius was, of course, using alternating current and transformers. Step the voltage way up for transmission, low loss, then step it back down to use safely. We all know that part.
Sure.
But the deeper insight, the real leap, wasn't just picking AC over DC. It was pure phase choreography. He used multiple coils, right, driven slightly out of sync, out of phase, a polyphase system. And this created what he actually called a rotating magnetic field.
A rotating field?
Yeah.
But nothing's actually rotating.
Exactly. It wasn't a static field pushing things. It was a traveling pattern of motion within the electrical substrate itself, you could say.
Ah, I see.
And what motion theory really highlights here is that the timing, the phase relationship between those coils, that was the fundamental carrier of energy, not just the raw voltage. And that understanding, thinking in terms of these moving patterns, allowed him to actually predict and engineer that rotating field, which, if you were only thinking static forces, wasn't obvious at all.
Right.
So from this motion theory view, a polyphase system, it's like a loop ensemble. The phases are deliberately offset.
A loop ensemble.
Yeah, and it's not just a metaphor. It means the field itself literally moves through space, even though no physical matter is moving along with it. And the whole grid then becomes this unbelievable continental metronome. Billions of machines, all kind of locked into and trained to this shared beat.
Wow, a continental metronome.
The result is just motion held coherent across impossible distances. Think about it. Niagara Falls to Manhattan, it wasn't just copper carrying volts, it was phase discipline, that precise synchronization holding its shape, propagating through the wire.
That's an incredible way to visualize the grid.
Yeah.
Which naturally brings us to maybe his most elegant creation, the induction motor.
Ah, yes. Beautiful device.
No brushes, no commutator sparking away, just clean rotation. A real revolution. How does that motor actually catch that invisible moving field you describe? How does it get into the rhythm?
Yeah, this is where the idea of entrainment is just so clear, so beautiful. The stator, right, the stationary part, that creates the rotating field we were just talking about.
Okay.
The rotor, the part that spins, it just naturally lags a tiny bit behind this moving field.
The lags.
Well, that slight difference in speed, that tiny desynchronization between the field's rotation and the rotor's rotation, that's what induces currents inside the rotor itself.
Ah, induced currents. Okay.
And those induced currents create their own magnetic field, which interacts with the stator's field, producing the torque. It pulls the rotor along, always trying to catch up. It's constantly trying to entrain with the stator's rhythm.
So it's chasing the field.
Exactly. In motion theory language, you've got a bounded loop. That's the rotor sitting inside this traveling sync gradient. That's the stator field.
Right.
That little bit of desync, the lag, that's what induces the currents. It creates this constant phase pull, trying to get the rotor perfectly in sync.
And the torque is the effort to sync up.
Precisely. Torque is kind of the price paid to close the phase gap. It's the energy needed to keep the rotor chasing that rhythm. And this was really the first mass-market device to take pure field motion, this invisible pattern, and turn it into useful mechanical work, so elegantly, so reliably.
Amazing. A constant dance of catch-up. But he didn't stop there. He also figured out how to, as you put it, edit the rhythm of electricity. Transformers. Tuned circuits. How does that fit the motion framework? What's the insight there?
Absolutely a transformer. Well, from this viewpoint, it's basically just two coils sharing a magnetic motion loop. Simple as that.
Sharing a loop. Okay.
And by changing the number of turns on the coils, which is just geometry, right? You change the phase amplitude trade.
Phase amplitude true?
Yeah, voltage up, current down, or the other way around. You're tweaking the proportions of the motion. Is the rhythm intense but localized? Or spread out but less intense?
Ah, okay. Manipulating the shape of the motion.
Exactly. And then you bring in capacitors and inductors, you put them together just right, get them resonating. Now you've got tuned circuits, oscillators, filters.
Right. The basics of electronics?
Yeah, but motion theory sees them a bit differently. An inductor. It stores motion as a circulating field. Think magnetic field energy. A capacitor. It stores motion as separated phase. Think potential energy in an electric field.
So both are storing structured motion.
Exactly. Or tension in the field structure. It's not just passive storage. And when they resonate, energy just sloshes back and forth between them super efficiently. Minimal loss. They say the loop purity is maximized.
Loop purity.
Yeah. And this whole idea of selective synchronization, being able to pick out and amplify specific rhythms, filter others out, that's the absolute foundation for radio, for phones, for, well, the whole information age, really.
Which leads us perfectly to the Tesla coil, you know, that iconic image, the crackling lightning.
Yeah.
It still wows people. How is that resonance as amplifier? What's the motion theory take on that spectacle?
Oh, the Tesla coil is just a brilliant, dramatic demonstration of coupled resonance. Basically, you have two resonant circuits, primary and secondary, linked loosely. You drive them right at their shared natural frequency.
Their sweet spot.
Exactly. And energy doesn't just flow through. It kind of sloshes back and forth between them. But because of the way they're designed, the energy builds up, climbs dramatically in amplitude, especially in that secondary coil.
Builds and builds.
Until it literally spills out into the air as those streamers, those sparks.
Okay, but how does motion theory see that?
It sees the coil as a resonant escalator. Each pulse of energy you put in isn't just added randomly. It's phase-aligned motion. It's added precisely in time with the existing oscillation in that shared loop.
Adding energy in sync.
Right. Pushing the field intensity higher and higher with each cycle until the air itself, which is normally an insulator, it actually entrains and conducts.
The air entrains.
Yeah. The reason it's so spectacular is you're literally seeing the medium, the substrate around the coil, accepting a new rhythm. The space becomes conductive, just for a moment, because the local sync density goes critical. The organized motion just gets too intense for the air to resist. It's a visual confirmation.
Wow. Okay, that makes sense. Now, the really big one. Tesla's grandest dream, maybe his most controversial. Global wireless power. Wardenclyffe Tower.
Ah, Wardenclyffe, yeah.
What does all this mean for wireless power today? Looking through that motion theory lens, did he get it right, or did he miss something fundamental?
Well, this brings up a really important distinction. Right? There are really two different physical ways wireless power works.
Okay.
First, there's near-field coupling. That's things like inductive charging, like the cheap pad for your phone, or capacitive coupling, is short range, can be very efficient if it's tuned right. Oh. And essentially, you're directly sharing a loop of oscillating energy between the charger and the device.
Sharing a loop, like the transformer coil.
Kinda, yeah. From a motion theory view, you're setting up a strong, local, rhythmic connection. Very direct.
Okay, near field, what's the other?
The other is far-field radiation. Think radio waves, broadcast power. This can go long range, obviously. But the energy spreads out, right? Like ripples in a pond. So the efficiency just plummets, unless you can focus it intensely.
Like with antennas or dishes.
Exactly. You need to really focus and phase the energy. In the far field, you're essentially casting a rhythm out into space and just hoping that a remote loop, an antenna somewhere else, manages to phase lock onto it.
Hoping it catches the beat.
Right. And that takes serious engineering. Big antennas, keeping the waves perfectly coherent, precise aiming. Now, Tesla, he pushed both of these boundaries, sometimes, arguably, beyond what the materials and the math of his time could really handle reliably.
Right.
But his core idea, his claim that power is a problem of phase geometry, that insight has actually aged perfectly. It's spot on.
How so?
Well, look at modern tech. Key charging is near-field coupling done well. Phased array radar, the MIMO antennas in your Wi-Fi router and 5G phone. That's all about manipulating phase geometry for the far field. They're quiet vindications of his fundamental thinking.
So his core insight about phase and geometry holds up, even if Wardenclyffe didn't transmit global power.
Exactly. The principles were sound. The scale and maybe some practicalities were the challenge.
And it wasn't just power transmission, right? There's that amazing story, him piloting a radio-controlled boat, Madison Square Garden, 1898.
Yeah, the teletomaton. Incredible demonstration.
Seems like just a cool gadget, but was it more than that through this lens?
Oh, absolutely more. It wasn't just remote control. It was proof of behavior at a distance, achieved through phase-coded coupling.
Phase-coded coupling.
The commands he sent weren't just on-off signals. They were specific rhythm signatures, patterns of pulses, synchronized in a certain way that the receiver on the boat was designed to recognize and lock onto.
Ah, so the boat was listening for a specific rhythm.
Exactly. Motion theory would say communication is selective entrainment under noise.
Yeah.
You pick out the intended rhythm from all the background chatter. I mean, Claude Shannon put the math to information theory later, but Tesla staged the first public performance of it.
Wow. And then there was his work out in Colorado Springs. Earth resonance. That sounds pretty out there.
Well, yeah, it sounds dramatic. But he was essentially, maybe intuitively, poking the planet's drumhead, trying to find its natural resonant frequencies.
The Earth has resonant frequencies.
Oh, yeah. Any bounded system does. The space between the Earth's surface and the ionosphere acts like a cavity. It supports these global electromagnetic modes. We call them Schumann resonances now.
Schumann resonances, right.
He didn't have the tools to measure them like we do today, but his intuition was likely pointing him there. Motion theory understands that any finite structure, like that Earth ionosphere cavity, will have preferred sync patterns, natural rhythms it likes to vibrate at.
And he was trying to excite those.
Seems like it. If you drive a system cleanly with the right rhythm, the whole field structure can respond and resonate. He was searching for the planet's natural beat, you could say.
Okay, now, we do have to touch on the areas where maybe his vision didn't quite pan out, or at least hasn't yet. Global power beaming, free energy, these ideas persist.
Right, the more controversial side.
From this motion theory perspective, why did he overreach there? And is there still something useful in understanding why?
We'll take global power beaming, like transmitting usable power wirelessly over thousands of miles. From a physics standpoint, doing that efficiently without, frying everything in between, it requires extreme coherence control.
Meaning?
Meaning keeping the beam perfectly focused, perfectly in phase over enormous distances. Think phased megastructures, gigantic antenna arrays, maintaining synchronization with incredible precision. We just don't have anything like that. Maybe it's possible in principle, but it's wildly impractical right now.
Okay, so coherence is the big hurdle for long-range power. What about free energy?
Yeah, the free energy rumors.
Mm-hmm.
That mostly comes from a misunderstanding of physics, I think. Any real device needs a source. It needs to tap into some kind of motion gradient.
A gradient, like a difference?
Yeah, like the electrical grid providing potential difference,
Yeah.
or the sun providing thermal difference, or wind providing kinetic difference. You need an imbalance to draw energy from.
Right, energy isn't created, just converted.
Exactly. Now, does the quantum vacuum have structure? Does it have energy? Yes. But effectively grabbing it, extracting net energy, likely requires a kind of phase leverage, a way to coherently interact with it that we haven't come close to engineering. Or it might just obey conservation laws like everything else.
So motion theory doesn't support the free energy claims.
Not in the sense of violating conservation laws. What it does say is keep the resonance in sight, because that part is incredibly powerful. Use Tesla's inspiration to drive better phase engineering, smarter ways to manage energy and synchronization, but let's constrain the claims to what's physically plausible.
That makes sense. Keep the useful core, ground the speculation. What's really fascinating, though, is how many actual modern technologies seem to echo these core ideas. Sometimes maybe without the engineers even thinking Tesla.
Oh, absolutely. It's everywhere once you look for it through this lens. Think about phased array radar systems, or 5G base stations, or the MIMO tech in your router.
MIMO, multiple input, multiple output.
Right. They all work by precisely controlling the phase of multiple antenna elements to steer beams, to focus energy, to send multiple data streams. It's programmable phase. It's basically Wardenclyffe with math in modern electronics.
Huh. Wardenclyffe with math. I like that.
And look at key wireless charging or other resonant charging systems. That's near-field loop sharing, just done safely and efficiently for consumer devices.
Right. Practical application of the near-field idea.
Even the research pushing for wireless power over slightly longer distances, you see things like strongly coupled resonant relays, special metamaterial waveguides. It's all about managing and guiding these rhythmic energy patterns.
And the grid itself.
The grid,
Yeah.
maintaining synchronization across continents, keeping that 50 or 60 hertz beat perfectly stable, especially as we add more variable renewables and lose some of the old rotating mass from big power plants. That's a massive ongoing challenge in keeping the beat. It's phase engineering on a continental scale.
Even fusion.
Yeah, even in fusion research, trying to confine that incredibly hot, unstable plasma. They use magnetic fields, of course, but they also battle these wild oscillations, these MHD modes. And one way they try to tame them is with phase-lock drives, injecting specific frequencies, specific rhythms to counteract the instabilities. It's Tesla's instinct applied at a nuclear level, almost.
Amazing. So this perspective doesn't just explain the past, it points to the future. You mentioned falsifiable hooks, new scientific avenues inspired by this upgraded Tesla.
Exactly. We can move beyond just interpreting history and actually test some predictions. For example, you could propose a coherence-distance law.
Okay.
Maybe in chains of strongly coupled resonators, the efficiency of power transfer over distance isn't just about classical coupling strength, but is built predicted by some metric of phase coherence along the chain. Motion theory would suggest that. You could build a lab setup and actually test that prediction.
Testable. Okay. What else?
Or think about ambient mode harvesting. Cities are flooded with RF energy, AC fields. Motion theory suggests these aren't just random noise. There are probably stable, persistent mode maps based on the geometry of buildings, wires, etc.
Standing waves, almost.
Kind of. So, maybe tuned multi-resonators, designed to align with these persistent ambient modes, could harvest energy more effectively or stably than devices just looking for the strongest single signal. Another testable idea.
Interesting. Harvesting ambient rhythms.
And one more, maybe grid phase therapy. Instead of just brute force control systems, could you inject very small, carefully calculated phase-dither patterns at key points in the grid, little rhythmic nudges to actively damp out those troublesome inter-area oscillations faster than current methods allow?
Using phase to stabilize the grid proactively.
Right. If ideas like these hold up under rigorous testing, then this Tesla-style phase engineering viewed through motion theory really moves from being, historical curiosity or showmanship into a potentially powerful new control science, applicable everywhere.
So wrapping this deep dive up, it really feels like Tesla's genius wasn't magic. It wasn't lightning bolts from his fingertips. It was this incredibly deep recognition that that everything useful we do with electricity is synchronization control.
That's it, exactly. He talks civilization, how to do things with fields by managing their rhythm, how to rotate them, capture them, step their intensity up or down, tune them, filter them, fling them across space, and sometimes, yeah, even sing through them with radio.
Right.
And motion theory, this lens we've been using, it doesn't need to mythologize him. It actually helps decode him. It reveals him as, like you said, the prototype phase engineer.
The original phase
Yeah,
engineer.
the hum of the grid. That's his beat, quite literally. Motors everywhere turn in his conceptual wake. Radios, wireless tech, they all whisper in the language he helped make common. Entrain, detune, retune, amplify, radiate.
He wasn't chasing magic.
No, he was listening.
Yeah.
Listening for the motion that wanted to happen in the electromagnetic field, and then he built the metal that let it dance.
Yeah.
He provided the structure for the rhythm.
That's a beautiful way to end it, and it leaves us and you with a provocative thought. What other unseen rhythms are out there all around us just waiting for someone to figure out how to build the right kind of metal to let them dance to?